Hi and welcome to our presentation for the 2021 ICSI conference. My name is Arvid Trapp. Together with Fabian Hollweck and Peter Wolfsteiner, we're presenting our research on the transmission of non-Gaussian random loading through linear structures. Let's begin with what to expect. The central goal of our research is to extend linear systems theory for the spectral decomposition of the kurtosis. This is provided by the fourth-order trispectrum belonging to higher-order spectral analysis. It could take hours to explain all details of higher-order spectral analysis. Therefore, we give a short overview, mainly in the paper. Central aspect to this presentation is to show a visualization tool which allows to meaningfully work with the trispectrum. The main scientific contribution, and which will be the third aspect, is to compare different kurtosis control algorithms. They allow to reproduce random loading given by a PSD and a given kurtosis value by different mechanisms. We will use the trispectrum to compare the decomposition of this kurtosis and see that it transfers differently through linear structures, mainly considering the nonlinear non-Gaussian model and the non-stationary non-Gaussian model. This slide provides a short visual motivation. Here you see two random loadings which may be used to assess the structural integrity of a dynamic structure. The upper one is a measured load representing real in-service loading. When calculating the power spectral density, the PSD, from this load, we end up with this average power spectral density. On this basis, we are able to derive a stationary Gaussian realization of same PSD, which is shown here. So both loadings have the same PSD in common. The PSD may be used in linear systems theory to estimate structural responses given the resonance behavior of a mechanical structure. It allows to assess how Gaussianity, the variance, transfers through linear structures. However, it does not allow to estimate how non-Gaussianity, specifically the difference between the two loadings, transfers through linear structures. To summarize the prior slide, here you see the Gaussian probability density function, PDF, which is fully defined by variance and mean. Variance belongs to the central moments. It equals the second-order central moment. They have a spectral density, which is the power spectral density. It can be interpreted as how much each frequency contributes to the full variance, respectively the full second-order central moment. In linear systems theory, an excitational PSD is correlated with the structural transfer behavior to estimate structural responses. In the case of the non-Gaussian load, the most popular descriptor is the kurtosis, which is defined as the standardized fourth-order moment, standardization, fourth-order moment. And this fourth-order moment also has a spectral density which is seldomly used, mainly because it's complex. It is a multidimensional metric. However, it provides essential information on how non-Gaussianity transfers through linear systems. So central moments may be used to describe the PDF of a random variable. Using higher order central moments allows to specify the non-Gaussianity of a random variable. Hereby, spectral analysis provides the frequency decomposition of those central moments. However, the main challenge of higher order spectral analysis is that with every order, the dimensionality of those spectra extends. This makes them very hard to calculate, visualize, and interpret. Usually it takes a long talk to introduce higher order spectral analysis. Here we included two simple graphics. The first shows some basic principles of signal processing that makes higher order spectral analysis so appealing, which is that they provide a frequency decomposition, a spectral analysis of probabilistic metrics by cross-frequency correlation. The second refers to the Fourier transform, which provides the basis of spectral analysis. The power spectral density is a full characterization of stationary Gaussian loading, here visualized by the bell curve. It is based on the amplitude information of the Fourier transform. However, higher order spectral analysis further includes the phase information, which is essential to calculate cross-frequency correlation, which make up these central moments. Let's face the challenge of visualizing the trispectrum. We begin with a couple proposals from literature. The first on the left-hand side, using color and size to highlight the highest entries. A more quantitative approach is seen on the right-hand side, slicing the full trispectral set along a single frequency axis and showing each in the two-dimensional plane using the color to indicate the function value. However, you can understand this rather as something to include in publications. For practical use and to meaningfully work with the trispectrum, it makes sense to have something like a graphical user face. This was developed as part of our research and will be presented in the following by Fabian Hollweck.
My name is Fabian Hollweck, and I am happy to present a MATLAB tool enabling the user to visually evaluate trispectra and cumulant spectra. In order to use it, a trispectrum which has been created according to the previously mentioned procedure has to be available to be loaded into the tool. First, we want to focus on visualizing and manipulating the trispectrum of one load series. To begin, the trispectrum to be evaluated can now be selected via the input signal drop-down menu. After choosing the resolution, or more specifically the number of the frequency bins, the trispectrum can be loaded by pushing the load button. As it is loaded, the load series and the corresponding statistical characteristics can be plotted in a separate window by pushing the plot signal button. The view panel enables the user to rotate the three-dimensional trispectrum by manipulating the azimuth angle and the height angle. The spectrum drop-down menu lets the user decide between the visualization of the trispectrum and the visualization of the cumulant spectrum, in which the decomposition of the kurtosis, respectively the excess kurtosis, can be examined. Further, the symmetries tick box lets the user suppress all symmetry areas by only visualizing the primary zone. To be able to cut off small fourth-order statistical moment entries in the spectra, the threshold limit can be increased with the threshold slider. To emphasize rather high or low values, the representation drop-down menu offers a linear default representation, a logarithmic representation to enlarge high-valued entries, and a natural logarithmic representation to diminish high-valued entries. A scaling slider can then be used to further enlarge or demagnify the fourth-order statistical moment entries for better visibility. When a meaningful representation of the trispectrum has been created, the desired trispectrum can be exported in several formats.
So far, we have taken a look at the input trispectrum, the spectral decomposition of the input loadings kurtosis. The integration of linear systems theory is straightforward. It functions just the same way as the calculation of the trispectrum. However, instead of being based on the finite Fourier transform of the input load series, it is based on the linear transfer function to define a transfer spectrum. This will be integrated in the second part of the visualization tool.
In the second part of the tri-spectrum tool introduction, the possibilities of alternating the transfer behavior and the effects on the structural response are being shown. To do so, the transfer function tab is selected. Here, a synthetical signal degree of freedom transfer function is being used initially. The implementation of a unimodal bandpass, or also a bimodal bandpass, demonstrates two simple discretized bandpasses with one or two resonances. Being able to select a custom transfer function gained from a specific structure is a very important feature and will be implemented soon. To adjust the single degree of freedom transfer function, the first eigenfrequency as well as the damping ratio can be alternated. The transfer function trispectrum is being matched to the adjustments automatically. Likewise, the unimodal bandpass can be modified in its resonance frequency as well as its bandwidth. The second resonance frequency can be used to shift the second bandpass of the bimodal transfer function. More features will be shown using the single degree of freedom transfer function. A transfer function threshold slider improves the view of its spectrum. By increasing it, the resonances in the trispectrum become visible. Further, the structural response trispectrum gets updated automatically depending on the used transfer function. Lastly, the examined transfer function can also be exported in various data formats.
In the following, the visualization tool is used to compare different kurtosis control algorithms. They allow to define random loading by a PSD and a kurtosis value. However, due to their different mechanisms, they produce a kurtosis which has a different spectral decomposition. And this spectral decomposition is essential to calculate the structural response. In the following, we compare two different kurtosis control algorithms. The first is based on a Gaussian stationary principle, which is subjected to a nonlinear transformation. This is called the Hermite polynomial transform procedure. The second one is based on non-stationarity and uses amplitude modulation to generate a specific kurtosis value. In the following, both are compared regarding the spectral decomposition of the kurtosis and how this affects how the non-Gaussianity is transferred to linear structures. We will see that they lead to quite different results.
The last part of the tri-spectrum tool introduction deals with comparing load series. In order to be able to compare two signals, a second input can be loaded within the Signal 2 tab, which has been already prepared beforehand. In the middle panel, the current transmissibility of the excess kurtosis is being calculated by putting both excitation excess kurtosis values and the structural response excess kurtosis values into proportion. Therefore, it is especially useful to show the cumulant spectrum representations of both signals. For better visibility, the threshold values for excitation and structural response have been increased. The transfer function tab includes two routines which manipulate the transfer function to compare both load series. Pushing the upper button sweeps the bandpass from the minimum frequency along the frequency axis up to the maximum frequency. On the right plot, an evaluation of the transmissibility is created, depicting how the particular transmissibilities of both signals behave. The transmissibility can be tracked on the y-axis, while the lower bandpass frequency occupies the x-axis. The changing transfer function can also be observed in the three-dimensional representation. Pushing the lower button lets the bandwidth of the bandpass expand in both directions until the full frequency space is covered. This stands for the full transmission of the excitation signal without any bias. Analogously, the y-axis of the right plot shows the transmissibility, as the x-axis represents the bandwidth. The three-dimensional transfer function shows the expanding resonances until the complete frequency space is covered. As shown before, all recorded plots can eventually be exported.
This slide contains the results of the last analysis in more detail. It has on the x-axis the bandwidth of the ideal bandpass filter. A very narrow bandpass approximates the resonance behavior of mechanical structures. On the y-axis, it contains the ratio of the output kurtosis to the input kurtosis. As you can see, the generating mechanism that is based on non-stationarity is not affected at all from the increasing bandwidth. However, for the nonlinear model, it transfers only partially in the response. Therefore, one has to take great care when choosing the proper generating mechanism. Let's summarize this presentation. To understand how non-Gaussianity transfers through linear structures, higher order spectral analysis has to be used. It must be coupled with linear systems theory. Hereby, a proper visualization technique is key. The resulting findings support and give the background to experimental data, which has shown that the nature of the loading's kurtosis, the non-Gaussianity, is crucial for the resulting structural responses and fatigue damage, and therefore for the lifetime of a structure.